Whoa! A rotation, a volume by rotating around an axis of revolution. This one says volume of a solid is generated when a region in the first quadrant is bounded by the graph of that guy, x to the third. We're all familiar with what x to the third looks like. The x-axis and the vertical line, x equals dose. And it's revolved around the x-axis. That's nice, because if it's revolved around the x-axis, we won't have to do for this one in particular, we wouldn't have to do like a washer method or anything like that, because the area touches the x-axis. So let's see what that looks like. This is about what x to the third looks like. I don't really care what's going on over here, because we know that we're just in the first quadrant. And then we have a vertical line at 2, and so that makes this our area that we are rotating. We're going to rotate around the x-axis like this, and then we might get a solid that kind of looks like this. And I tried to draw like one of the cross sections that's formed. Whenever we do a rotation, we always get circles for cross sections. But the formula stays the same. What you're going to do is you're going to take the integral of the area function. And in this case, because our axis of revolution is horizontal, that means our integral is going to be with respect to x. All right, so we got to make sure we start out with our, not start off with whatever. I don't know why I said that. But anyways, we have the lower bound and the upper bound. Can't forget that guy. And then we must define our area function. Now, because it's a revolution, we know it's going to be a circle, and we know that the area of a circle is simply pi r squared. Yay! Okay, but this function, this area function must be written in terms of x, because our the cross sections are perpendicular to the x. And so what is r? What is the radius in terms of x? That's what we're thinking about right now. What are we going to put in there into those parentheses? Now, if you're just looking at this circle, maybe it makes a lot of sense to you. The radius always starts at the axis of revolution, and then it goes up to the outer curve or whatever curve you're revolving, in which case it's x to the third. And so that's going to be our radius. If we simplify this guy really quick, it'll be pi x to the 6. So when we throw this into our integral, we can take the pi out because he's a scalar. And then we can integrate the x to the 6. And so the antiderivative of x to the 6 is 1/7 x to the 7th, because we add 1 to the 6, and then we divide by the 7. Then we have to plug in the 2 and the 0 and subtract them. It's always top minus bottom. All right, so we have pi times this. And then that, I love the second one. I love it when the bottom one is 0, because it just goes away. And so I have 128 pi over 7, which gives us our answer. All done.